In the previous class, we have discussed about van der Waals equation. Today, we continue with the same. Okay, so the syllabus is up to van der Waals equation. Okay, ma. So in this case, now what we have understood already, van der Waals equation is for real gases. Van der Waals equation is for real gases. The scientist van der Waal has introduced what? He has introduced what pressure correction and volume correction. Pressure correction and volume correction both are added to what? Ideal gas equation to get real gas equation. Okay. So yesterday we have discussed different conditions, case 1, case 2, case 3 like this. At extremely low pressure and extremely high temperature, low pressure like this conditions we have discussed. Okay, ma. So now today we are going to discuss about what? Merits of van der Waals equation. Merits means what here? The what here? Advantages of this van der Waals equation. The van der Waals equation holds good. It holds good for real gases. It holds good for real gases up to moderately high pressures. Okay, moderately high pressure means what? Not very high pressure. Not very high pressure. At very high pressure, it is not applicable to real gases. Okay, at extremely low pressure also it is not applicable to real gases. At extremely low pressures and extremely high pressures, it is not applicable to what? Real gases. It is applicable to real gases only at intermediate pressures. Intermediate pressure meaning what? Neither very low pressure nor very high pressure. That is intermediate pressure we see here. Is that clear? Ma? So next, the equation, van der Waals equation. Okay, van der Waals equation represents what? The trend of the isotherms. Isotherms means the graphs plotted at constant temperature. So the equation represents the trend of the isotherms, representing what? Representing the variation of PV, the variation of PV with P, variation of PV with P for various gases, for various gases. So when you plot a graph of PV versus P, we get a straight line parallel to what? X-axis. This is for ideal gas. It is for ideal gas. And if we take real gas, what happens? It will be like this. For real gas, it will be like this. Real gases will deviate from this ideal behavior. So this type of isotherms at constant temperature, this curve is called what now here? Isothermal curve. So isothermal graph. So about these isotherms, which explains here, this van der Waals equation explains. These are merits of what now here? Two merits of van der Waals equation and third merit now. So now in this case now here, from from van der Waals equation, from van der Waals equation, it is possible to obtain, okay, expressions of Boyle's temperature. Expressions for what here? Boyle's temperature. So from the van der Waals equation is given by P plus an square by, so P plus an square into, sorry, what is our equation? Tell me. P plus an square by V square na, into V minus NB. V minus NB is equal to what? nRT. It is van der Waals equation. So in this van der Waals equation, A and B are what? A and B are constants. A and B are the constant values here. So by using these constant values A and B, we can express what now here? Boyle's temperature. So this Boyle's temperature is given by what? Expressed by what? TB. T capital B indicates what now here? Boyle's temperature. So TB indicates what? Boyle's temperature. Okay. And then critical constants. Critical constants are what now here? Critical pressure. We are going to discuss about this in next classes. We discuss about this. So critical pressure, critical temperature, critical pressure, critical temperature, and critical volume. Critical volume, critical pressure, critical temperature. About these three we'll discuss in the next classes. Okay. So now we can express what and what here? By using van der Waals equation, we can express Boyle's temperature. Already Boyle's temperature we have discussed. Boyle's temperature is equal to A by RB. I told you. A by RB. So A is what now? Van der Waals constant, which is the measure of what? Attractive forces between gas molecules. And B is what? Van der Waals constant, which is the measure of size of gas molecule or volume of gas molecule. R is universal gas constant we studied. So by using these, we can also express what critical constants. The critical constants are nothing but critical pressure PC, critical temperature TC, critical volume VC. So these are all things we'll study in the next class. Okay. And also we can express what inversion temperature. Inversion temperature. Inversion temperature means TI. TI. TI indicates what inversion temperature. So about this also we'll discuss. Okay. But these all not there. Critical constants not there. Inversion temperature not there for this examination. Coming exam, these critical constants will not be there. But remember that these critical constants can be expressed by using what? Van der Waals equation. In terms of what? In terms of the Van der Waals parameters A and B. Van der Waals constants means Van der Waals parameters. By using A and B, we can express the formula of critical temperature, inversion temperature, Boyle's temperature, and also critical pressure, critical volume. Okay, ma. So these are all things we are going to discuss. Okay. Next, Van der Waals equation. Van der Waals equation is useful in obtaining a reduced equation state, a reduced equation of state. So Van der Waals equation is useful in getting what now here, in obtaining what? A reduced equation of state, which being a general equation of state has, which has the advantage that a single curve can be obtained for all gases, for all the gases, when the equation, when the equation if graphically represented by plotting the variables. By plotting variables means what now here? Different pressure, different volume, these are all variables. What are A and B? A and B also variables for different gases. A and B also different gases. So simply remember that we can use this Van der Waals equation to obtain what? A reduced equation, a reduced equation of state, a reduced equation of state, about which we will study in higher classes. So these are all things we are not going to discuss in detail, but remember simply one statement that Van der Waals equation is useful in obtaining a reduced equation of state. Okay, so in which a single curve is enough, a single curve is enough to explain what? Different types of gases. Okay, so about which you will study in higher classes, higher studies. Okay. Next, now what we studied so far are merits. Merits of what? Van der Waals equation. Now it is limitation. Limitation of what? Van der Waals equation. Limitation of Van der Waals equation. Limitations meaning what here? The drawbacks. The drawbacks are shortcomings. We can say the limitations means what now? Drawbacks or shortcomings. Also we can say here. So the limitations of Van der Waals equation. First one, this equation, Van der Waals equation, shows appreciable deviations. It shows appreciable deviations at too low pressures, too low temperatures, and high pressure also. At high pressure and low temperatures. At very low temperature and at very high pressure, the deviations will be more. Deviations will be more. So under conditions of what now here? This low temperature condition and high pressure condition, real gases, real gases deviate, real gases deviate to the maximum extent, real deviate to maximum extent. So maximum extent of deviation will be shown by real gases at what conditions? At very low temperature condition, at very high pressure condition. When the real gases behave as ideal gases, I told you, at at very low pressure, at very low pressure and high temperature, at very low pressure and high temperature, real gases behave as what? Real gases behave like ideal gases, I told you. When real gases behave like ideal gases at low pressure, very low pressure and high temperature. But here what is given here? Reverse given, low temperatures and high pressures. Under these conditions, the real gases will be deviated to the maximum extent. More deviation will be shown by real gases. So under these conditions, the real gas behavior cannot be explained by this equation. Actually, Van der Waals equation is nothing but real gases, na? This equation for real gases. This equation is meant for real gases. So these real gases were not explained here. Okay, for these real gases under this condition is not shown here. Is that clear, ma? So for real gases at low temperature and high pressure, the van der Waals equation is not applicable. That point we have to understand. That is one drawback, limitation. After that, the values of van der Waals constants, that is A and B, small a and small b. The values of van der Waals constant A and B do not remain constant. They are not constant over the entire range of temperature and pressure. Okay, so they are not constant at the entire range of temperature and pressure. That means if you take a particular gas, in this gas, between the gas molecules, the attractive force will be there. Na? This attractive force between the gas molecules can be measured by what? A. A is what now? Attractive force between gas molecules. And the size of this gas molecule, the size of gas molecule or volume of gas molecule is what now shown by B. The value of B indicates what? Size of gas molecule, otherwise volume of gas molecule. So this A and B for a particular gas will not remain constant at different conditions of temperature and pressure. At all pressures and all temperatures, A value and B value for a given gas will not remain constant. That is another drawback of what this equation. Once again, check it here. The values of van der Waals constants A and B do not remain constant. They do not remain constant over the entire ranges of temperature and pressure. Hence, this equation is valid only over specific range of temperature and pressure. At the specific range of temperature and pressure only, A and B will be applicable to the gases. Is that clear, ma? So that point mainly you have to understand here. So there are drawbacks of what? Limitations of what? Van der Waals equation. Okay. Next. Now in detail we'll discuss about what now? The volume correction. The volume correction. Actually, what is the meaning of this volume correction and how he introduced what? Volume correction. Okay. So first one is what? Volume correction is shown by V dash. V dash indicates what? Volume correction. This volume correction is introduced by him, by Van der Waals, as what? NB, na? N into B is what? Volume correction. Okay. Now here see, Van der Waals assumed. I told you the scientist name is Van der Waals, not Van der Waal. Waals itself is name of scientist. So Van der Waals assumed that okay, molecules of a real gas are rigid. Okay, rigid spherical particles. They are rigid spherical particles. Each molecule is rigid and spherical particle according to Van der Waals, which the rigid molecules possess a definite volume. Each spherical molecule has what? The volume of 4 by 3 pi r cube. Each molecule sphere has what now? 4 by 3 pi r cube volume. This okay, thus the volume of a real gas, that is volume available for compression, or volume available for movement is therefore actual volume minus the volume occupied by the gas molecules. So this is V is what now here? Actual volume. So how to write now here? Volume of ideal gas is equal to volume actually available. Actual volume is observed volume. Actual or observed. Actual volume or observed volume. Okay. So the V actual minus what now here? Correction. The correction is given by NB. The correction is what here? NB. Correction for the volume is NB, and V is what? Actual volume available for compression. Actual volume available for compression minus okay NB is what now? Ideal gas equation, ideal gas volume. So the volume of ideal gas is equal to volume of real gas, that is actual volume minus volume correction. Now whose volume is more? Real gas volume is more than what? Ideal gas volume. Ideal gas is equal to real gas volume minus something, na? Therefore, which one is greater here? This actual volume is greater than real gas volume is greater than ideal gas volume. Okay. Next, if if B is the effective volume of the gas molecules per mole, okay, the ideal volume for the given gas equation is what now? V minus B. If you take 1 mole here, if you take if N is equal to one mole, then NB becomes what? 1B. V minus NB becomes what? V minus B. Okay, so instead of V, what we take here? V minus B. So V ideal is equal to what, ma? V minus NB. For 1 mole, it will be V minus B. Next one. So corrected volume. Corrected volume means what now here? Volume correction. Corrected volume VI. V ideal. V ideal. V ideal is equal to V real minus P. V ideal is equal to what, ma? V real minus B. So V real gas minus B. B is what now here? Correction for the volume. For 1 mole of gas. 1 mole of gas means N is equal to what? 1. And for n number of moles of the gas, V ideal is equal to V observed, that is V real minus NB. N is what number of moles. So this point we have to understand. B is termed the excluded volume. Excluded volume we can say, or co-volume we can say. Co-volume, otherwise excluded volume we say, which is constant. The B is constant and characteristic of each gas. That means B for a particular gas is a particular value, but for different gases B values will be different. The excluded volume B is actually, okay, four times the actual volume of the gas molecules. Okay, if you take 1 mole, in 1 mole, for 1 mole. 1 mole means how many particles will be there? Avogadro number of particles will be there. The Avogadro number of molecules will be there. Avogadro number of molecules will be present in 1 mole of gas. For 1 mole of gas, if you take B is equal to 4 times, okay, 4 times of the total volume of what? Gas molecules. So each gas molecule what? 4 by 3 pi r cube, na? Each gas molecule volume is what? 4 by 3 pi r cube. One gas molecule volume is equal to 4 by 3 pi r cube into how many molecules are there? Avogadro number of molecules in 1 mole. So Avogadro number of molecules into each gas molecule is 4 by 3 pi r cube into 4 times. So 4 times of the total volume of 1 mole of gas molecules is equal to B. So B is equal to what now here? The excluded volume B is actually equal to what now here? 4 times the actual volume of the gas molecules. The actual volume of the gas molecules of 1 mole, how much? Avogadro number of molecules into 4 by 3 pi r cube. Into how many times? 4 times. So that point you keep in mind. Next, so this is what here. B is equal to what now here? B is equal to 4 by 3 pi r cube each gas molecule volume into 4 times of Avogadro number N. N is what? Na. Next, where R is what? Radius of gas molecule. For each gas molecule, the radius is what? R. Radius is R. And N is what now here? Avogadro number. Here we write Na or N naught. N naught or Na. Avogadro's number. Okay, ma? Next, pressure correction now. Pressure correction is given by P dash. Now, how he introduced the P dash is equal to A into N square, by V square, where A is what? Constant. Magnitude of attractive forces between gas molecules A. N is what? Number of moles. V is what? Volume. So P dash, pressure correction, is equal to AN square by V square. So a molecule in the interior of the gas, okay, is attracted by other molecules on all sides. Suppose we say it is what now here? One container. In this container, one gas molecule is about to collide with the walls. One gas molecule is about to collide what? The gas container, means container walls. This gas molecule is moving and it is about to collide the walls of container to exhibit what? Some pressure. But around this molecule, there are different molecules in the interior. So this molecule attracts the molecule, and this molecule is attracted by another molecule. This is also attracted by another molecule. Like this, Around it, many molecules are there now. These all molecules of gas in the interior, in the bulk, will be attracting what? This given molecule. This particular molecule is attracted by many other molecules surrounding it. So now here, when the attractive force is acting on this molecule will be slowed down. The velocity of this molecule will be slowed down. Then it exerts less pressure on this wall. If attractive force is there between gas molecules, one gas molecule is attracting other gas molecule, and the velocity of this gas molecule will be reduced now. This gas molecule velocity will be reduced because of attraction by other molecules. That's why this gas molecule will exert less pressure on the walls, less pressure on the walls than expected. Okay, that point we have to understand here. So what they said is that a molecule in the interior of the gas is attracted by other molecules on all sides. These forces, thus are not effective. These forces are not effective as equal and opposite forces cancel each other. That means what now here? Here, this side one molecule is opposed. Here one molecule is attracting it. So this molecule is attracting this given molecule, and other side, opposite side, another molecule is attracting. So this force of attraction and this force of attraction, both will be cancelling each other, opposite sides. This force of attraction, this force of attraction, opposite sides force of attraction will be cancelling each other. Okay, so opposite sides will be cancelling. Suppose this is a molecule considered now. Here this side one force is acting, this side one force is acting. These two opposite forces will cancel each other. And see this one, here one force is acting, this side, here one force is acting on the given molecule. These two forces also will cancel each other. Like this, what now here, the force of attraction will cancel each other. Okay. Next, however, a gas molecule which is just going to collide the wall of the vessel experiences an inward pull due to what? Unbalanced attractive forces. See now this one here on this given particular molecule which is about to collide the walls of the container. On this molecule, different forces of attraction there. Because of this inward pull on this molecule will exert less pressure than exerted. Less pressure than exerted. Therefore, it strikes what? The wall with less momentum. Momentum is mass into velocity. Momentum formula what? Mass into velocity. Mass times velocity is what? Momentum. So the momentum is less of this given molecule. Therefore, the molecule strikes the wall. The particular molecule selected, observed, strikes the walls of the container with less momentum, and the absorbed pressure will be less. The absorbed pressure will be less than expected, less than ideal gas pressure. That's why the ideal gas pressure is equal to real gas pressure plus some pressure correction. Real gas pressure plus some pressure correction. So here this P absorbed is nothing but P real gas, pressure of real gas. So now pressure of real gas and pressure of ideal gas, which is greater? P ideal is equal to P real plus some pressure correction. That's why P ideal is greater than what? P real. In ideal gas, what now here? No attractive forces. In ideal gas, no forces of attraction. In ideal gases, no forces of attraction. When there are no forces of attraction, this molecule, if you take around it, this particular molecule is not experiencing any inward pull by these molecules. These molecules not attracting this particular molecule, no attractive forces. That's why on the wall, this will be exerting more pressure. In case of ideal gas, particular gas molecule, when you select, this gas molecule is not attracted by other molecules in ideal gas. No attractive force between the gas molecules. Therefore, it will be exerting more pressure on the walls, ideal gas. But if you take real gas, in real gas, what now? This particular gas is attracted by other molecules around it. This is why here this will be exerting less pressure on these walls. This molecule of real gas will exert less pressure on the walls because of attractive forces. But here in ideal gas, on this molecule, no attractive forces. Therefore, it exerts more pressure. That's why the P ideal is greater than what? P real. P ideal, P ideal gas is greater than what? P real gas. So this concept you have to understand here. Okay, ma? So next, so where P dash is what? The pressure correction. P dash is pressure correction. That point keep in mind. So next now here, the pressure correction. The pressure correction depends upon two factors mainly. The attractive force exerted. The attractive force exerted on a single molecule. The attractive force exerted on this single molecule, like this here. Different attractive forces there now. The attractive force exerted on a single molecule about to strike the wall is proportional to the number of molecules per unit volume in the bulk of the gas molecule. Suppose on this gas molecule, if more molecules are surrounding, okay, around this gas molecule, if more molecules are surrounding, now pressure exerted will be less. On the wall of container, the pressure exerted will be less if this gas molecule is attracted by more molecules. Around this particular gas molecule, if larger number of gas molecules are there, they will attract this given molecule. Now, when attractive force on this molecule is greater by other molecules, less pressure will be exerted. Less pressure will be exerted. That's what they are saying. So more the number of gas molecules around this, less will be pressure exerted. That point keep in mind. Next, the number of molecules striking the wall, which is also proportional to the number of molecules per unit volume of the gas. That means what here? So on this wall here, more molecules are there means more pressure will be exerting. If number of molecules is greater, if number of gas molecules is greater in the given gas, more number of collisions will be there on the walls. On the walls of container, more will be the number of collisions. If number of molecules is greater, then more pressure will be exerted. So what they're saying, second point, the number of molecules striking the wall, okay, is also proportional to the number of molecules present per unit volume of the gas. Per unit volume of the gas, if more number of molecules are there, more number of collisions on the walls, therefore more pressure will be exerted. Okay, so more the number of gas molecules in the given gas, more pressure. Plus, if a given molecule that is going to collide, the particular molecule which is going to collide the walls is surrounded by more molecules, more attractive forces on this. If this molecule experiences more attractive force by other molecules, less pressure will be exerted because this molecule is pulled by other molecules now. Therefore, less pressure will be exerted on this. So these points we have to understand clearly. Next, both these factors are proportional to the density of the gas. So both these factors will depend on what density of the gas. Therefore, the attractive force is proportional to the square of the density of gas. The attractive force is the force of attraction. Pressure correction is what we are directly proportional to square of the density. So initially what we have to understand, pressure correction is directly proportional to total attractive force. Means the given molecule is attracted by many other molecules now around it. It is wall of the container. So it is exerting pressure on this wall. Now this molecule is experiencing more number of attractive forces. Okay, that's pressure correction. Next, the pressure correction is directly proportional square of the distance. Density. D is what here? Density. So density is equal to mass by volume. Na? Density is equal to mass by volume. Mass upon volume is equal to density here. Now here, in this case, d square we have taken. If you take d square, it is what now here? 1 by v square. 1 by v square per unit mass. Okay. If mass is constant for given mass of gas, for a given mass of gas, when mass is constant, yeah, d square is equal to what? 1 by v square. So in place of d square, what we can add? 1 by v square. So the pressure correction is inversely proportional to what? Square of the volume. and pressure correction is directly proportional to square of the density, and pressure correction is directly proportional to total attractive force on the given molecule. On the given molecule, total attractive force and pressure correction are directly proportional. Okay, so these points we have to understand. The same thing we can mention now. P dash means pressure correction. What is here? P dash means what here? Pressure correction. The pressure correction is equal to A by V square. A is what? Attractive force now. A is what? Attractive forces. The magnitude of attractive forces what? Given by A. So A divided by A value divided by V square. So P dash is equal to A by V square. For how many moles? For 1 mole. For 1 mole. 1 mole means what? Now N is equal to 1 na? Okay, N is equal to 1. If you take what here? N number of moles, we take different here. So where A is a constant depending upon the nature of the gas. Nature of the gas, and V is the volume of 1 mole of gas. V is what? Volume of 1 mole of gas. N is equal to 1. Thus, corrected pressure, that is pressure correction. The pressure correction P ideal is equal to total P ideal is equal to P real gas plus some correction. Okay, some correction is taken here. Next, so making both the corrections, the general equation PV is equal to RT, that is the ideal gas equation. This is what ideal gas equation. The ideal gas equation may be written as what? P plus A n square by V square. N square means 1 square here. Into V minus NB. V minus 1B is equal to 1 RT. N RT becomes what? 1 RT. It is for how many moles? For 1 mole. For 1 mole. Okay. Sometimes here, what will be taken? The equation is called Van der Waals equation for 1 mole here. And Van der Waals equation for n number of moles. For how many moles here? N number of moles is given by what? P plus an square by V square into V minus NB is equal to nRT. nRT. So here P is what now here? P real gas. And this V is what? V real, volume of real gas, pressure of real gas. And what is this total here? This total is equal to what now? V ideal. So V ideal is equal to volume of ideal gas is equal to volume of real gas minus correction. And this total is what now here? This total is what? P ideal. P ideal. So P ideal total is equal to what? P real plus an square by V square, pressure correction. So this point mainly remember. And sometimes remember here, sometimes what they ask you, if we take half mole, if N is equal to 1 by 2, half mole. 1 by 2 mole means what now? 0.5 mole. If N is equal to 0.1 mole, means 0.5 mole, 1 by 2, wherever N is there, what we substitute here? Whatever we take, okay, wherever N is there, we take what now? 1 by 2. So here N square becomes what now here in this case now? In this case, N square becomes what? If N is equal to 1 by 2, N square will be what now here? 1 by 2 whole square. N square will be 1 by 2 whole square, that is equal to 1 by 4. So wherever N is there, we substitute what? 1 by 2. N square becomes what? 1 by 2 whole square, that is 1 by 4. Okay, and sometimes they ask you if N is equal to 0.25 moles. 0.25 moles means what now? N is equal to 1 by 4 na? 1 by 4. 0.25 moles means what ma? 1 by 4 moles. If N is equal to 1 by 4 mole, then N square will be what now here? N square will be 1 by 4 whole square. Okay, 1 by 16. So like this, we have to substitute what now here? N value, like given for given number of moles. If 1 mole is given, N is equal to 1. If 1 by 4 moles given, N is equal to 0.25. If 1 by 2 moles given, N is equal to 0.5 mole, like this. So in this way, now for different number of moles, the Van der Waals equation should be written. So this is all about what? Van der Waals equation. I'm going to send you today this PPT. Please go through each and every point thoroughly. And also remember that after this, whatever we did not discuss, that points you don't take into consideration. whatever we have discussed, up to that only remember, up to that only study once again, and do all the material bits without any fail. Thank you, ma'am. Bye. Good day.